What if I told you that everything you have ever seen, everything you have ever touched, every single moment you have ever experienced, is nothing more than the thinnest possible surface of something incomprehensibly deeper? What if the ground beneath your feet, the air filling your lungs, the light hitting your eyes right now, is just the outermost skin of a reality so vast and so strange that the human mind was never designed to comprehend it? And what if I told you that right now, buried 100 meters beneath the border of Switzerland and France, inside the largest and most complex machine ever built by human hands, scientists are finding evidence that this hidden layer is not science fiction, not philosophy, not speculation, but something that the data itself is beginning to reveal. This is not a thought experiment. This is not a what-if scenario designed to entertain you for a few minutes and then fade away. This is the story of how the most ambitious scientific project in the history of our species began pulling at a thread in the fabric of reality, and what it found when that thread started to unravel. This is the story of CERN, the Large Hadron Collider, and the growing mountain of evidence that suggests our understanding of the universe is not just incomplete, it is fundamentally, profoundly, almost embarrassingly shallow. Today we are going to go deep, and when I say deep, I mean we are going to journey from the surface of what you think you know about reality, all the way down to the subatomic foundations where the rules themselves begin to break. We are going to talk about particles that wobble in ways they should not wobble. We are going to talk about mass measurements that defy the most successful theory in the history of physics. We are going to talk about a hidden universe called the zeptouniverse, a realm so small that even the most powerful machine on Earth can barely reach its doorstep. We are going to explore dark matter, dark energy, extra dimensions, parallel fields of existence, and a concept so radical that it suggests space and time themselves might not even be real, that they might be emergent properties of something even more fundamental hiding beneath them. And here is the thing that should keep you watching. Everything I'm about to tell you is grounded in actual data, actual experiments, actual results from actual physicists who have dedicated their entire lives to answering one single question. What is reality actually made of? The answers they are finding are not what anyone expected. They are stranger. They are more beautiful. And they are far, far more unsettling than any science fiction movie could ever dream up. Before we begin this journey, I want to set the stage with a few facts that should stop you in your tracks. The Large Hadron Collider at CERN is 27 kilometers in circumference. That is a tunnel so large that if you tried to walk around it, it would take you roughly 6 hours. Inside that tunnel, particles are accelerated to 99.9999999% of the speed of light. Let that sink in. There are almost no more nines you can add. These particles are traveling so close to the speed of light that from their perspective, time itself has nearly stopped. At the point of collision, temperatures reach over 5 trillion degrees, which is more than 100,000 times hotter than the center of the sun. And in every single second of operation, 600 million collisions occur inside this machine. When they discovered the Higgs boson in 2012, Peter Higgs, the man who had predicted its existence 48 years earlier in 1964, was sitting in the audience at CERN. He was 83 years old. When the announcement was made, he cried. He had spent nearly half a century waiting for the universe to confirm what his equations had whispered to him as a young man. And the universe, through this extraordinary machine, had finally said yes. But here is the part of the story that most people do not know. The discovery of the Higgs boson was supposed to be a beginning, not an ending. It was supposed to open the floodgates to a new era of particle physics, an era where one discovery would lead to another and then another, cascading into a revolution of understanding. Instead, something unexpected happened. The floodgates did not open. The new particles that theorists had predicted would follow the Higgs, the supersymmetric partners, the dark matter candidates, the extra-dimensional signatures. None of them appeared. And for several years, a quiet unease settled over the physics community. Had the standard model simply gotten everything right? Was there nothing more to find? Was this the end of the road? The answer, as it turns out, is no. Emphatically, beautifully, mysteriously, no. Because while the grand predicted discoveries did not arrive on schedule, something else did. Anomalies, subtle deviations, tiny cracks in the perfect facade of our most successful theory. And those cracks, those whisper-thin fractures in the foundation of physics, are now widening. They are pointing towards something beneath the surface, something hidden, and CERN is right at the center of it. If this is the kind of deep, mind-expanding science content that sets your brain on fire, then you are in exactly the right place. Hit that like button right now, because this video is going to take you on a journey that will fundamentally change the way you see the universe. Subscribe if you have not already, and turn on notifications, because the kind of content we create here goes places that other channels simply do not dare to go. And drop a comment right now telling me what you think is hiding beneath reality. I want to know your instinct before we dive in, because by the end of this video your answer might be completely different. Now, let us begin at the beginning. To understand what CERN may have discovered, you first need to understand what CERN actually is, why it exists, and what it was built to do. Because the story of CERN is not just a story about science, it is a story about humanity itself. It is a story about what happens when an entire species decides that it will not stop asking questions, no matter how difficult, no matter how expensive, no matter how terrifying the answers might be. The year was 1954. The world was still scarred from the devastation of 2 world wars. Europe, in particular, was reeling. The continent that had given birth to some of the greatest scientific minds in human history, Einstein, Planck, Bohr, Heisenberg, Curie, had also given birth to the most destructive conflict humanity had ever known. And in the aftermath, there was a profound and desperate need to find something, anything, that could unite nations not through force but through purpose. That purpose was science. 12 European nations came together and founded the Conseil Européen pour la Recherche Nucléaire, the European Council for Nuclear Research. They chose a site near Geneva, straddling the border between Switzerland and France, and they set out to build something that had never existed before, a laboratory dedicated not to building weapons, not to gaining military advantage, but to understanding the fundamental nature of reality. That laboratory is what we now know as CERN. Today, CERN is the largest particle physics laboratory in the world. It is home to 23 member states and hosts scientists from over 110 countries. More than 17,000 people contribute to its experiments. And at its heart, buried 100 meters beneath the rolling farmland of the Swiss-French countryside, lies the crown jewel of human engineering, the Large Hadron Collider, or LHC. The LHC is not just a scientific instrument. It is an engineering miracle. It is a monument to what humanity can achieve when it decides that knowledge is worth pursuing at any cost. The numbers alone are staggering. The main tunnel forms a circle 27 kilometers in circumference. Inside that tunnel, 2 parallel beam pipes carry streams of protons in opposite directions. 9,300 superconducting magnets guide these beams, bending them into their circular path with magnetic fields over 100,000 times stronger than the Earth's own magnetic field. These magnets are cooled to minus 271.3 degrees Celsius, which is colder than the vacuum of outer space. In fact, the LHC is the coldest place in the known universe, by design. When the machine is running, each beam contains roughly 3,000 bunches of protons, with each bunch containing around 100 billion protons. These beams are accelerated until they reach 99.999999% of the speed of light, and then they are steered into head-on collisions at 4 specific points around the ring. At each of these collision points sits a massive detector, a cathedral-sized instrument designed to capture and analyze the subatomic debris that sprays outward from each collision. The 4 main detectors are named ATLAS, CMS, LHCb, and ALICE. ATLAS and CMS are general-purpose detectors designed to study a broad range of phenomena. LHCb specializes in studying the subtle differences between matter and antimatter through the behavior of particles called B-mesons. And ALICE is designed to study a primordial state of matter called quark-gluon plasma, a superhot soup that existed in the first microseconds after the Big Bang. The cost of building the LHC and its detectors was approximately $13.25 billion. And let me tell you something, it was worth every single penny, and here is why. The purpose of the LHC is deceptively simple. Take particles, accelerate them to nearly the speed of light, smash them together, and then look at what comes out. When particles collide at these extreme energies, something remarkable happens. The energy of the collision, according to Einstein's famous equation E equals mc squared, can convert into mass. New particles are created from pure energy, particles that do not exist in the everyday world around us, particles that have not existed freely since the universe was less than a trillionth of a second old. By studying these particles, physicists are essentially recreating the conditions that existed at the birth of the universe. They are peeling back layer after layer of reality, looking for the most fundamental building blocks of everything that exists. And for decades, the framework they used to understand what they found was something called the Standard Model of Particle Physics. The Standard Model is, by any objective measure, the most successful scientific theory ever created by human beings. It describes 17 fundamental particles, arranged in a beautiful mathematical structure that account for every single interaction we have ever observed in the subatomic world. There are 6 quarks, which combine in various ways to form protons, neutrons, and a zoo of other composite particles called hadrons. There are 6 leptons, the most famous of which is the electron. And there are 5 bosons, force-carrying particles that mediate the fundamental interactions of nature. The photon carries the electromagnetic force. The W and Z bosons carry the weak nuclear force. The gluons carry the strong nuclear force. And the Higgs boson, the last to be discovered, is associated with the Higgs field, a field that permeates all of space and gives particles their mass. Without the Higgs field, atoms could not form. Without atoms, there would be no stars, no planets, no chemistry, no biology, no you, no me. The Higgs field is literally the reason anything has substance, and proving its existence was one of the primary goals of the LHC. On July 4, 2012, CERN made the announcement that the world had been waiting for. Both ATLAS and CMS had independently detected a new particle consistent with the Higgs boson, at a mass of approximately 125 gigaelectronvolts. The statistical significance exceeded 5 sigma, the gold standard in particle physics, meaning there was less than a 1 in 3.5 million chance that the signal was a statistical fluke. Peter Higgs sat in the audience, tears streaming down his face. François Englert, who had independently developed the same theory, sat beside him. Both men would share the Nobel Prize in Physics the following year. It was a triumph. an absolute, unqualified triumph. But it was also, in a very real sense, the last triumph of the old era. You see, the Standard Model, for all its breathtaking success, has a problem. Actually, it has several problems. And these problems are not small. They are enormous. They are the kind of problems that keep theoretical physicists awake at 3 in the morning, staring at equations that refuse to balance, wondering if everything they thought they knew was just an approximation of something deeper. First, the Standard Model does not include gravity. This is not a minor omission. Gravity is one of the 4 fundamental forces of nature, and the Standard Model simply has nothing to say about it. Einstein's general theory of relativity describes gravity beautifully at large scales, planets, stars, galaxies, but it breaks down completely at the quantum level. And the Standard Model describes the quantum world beautifully, but it cannot incorporate gravity. These 2 pillars of modern physics, general relativity and quantum mechanics, are fundamentally incompatible. They speak different mathematical languages. They make different assumptions about the nature of space and time. And nobody, despite decades of effort, has figured out how to unify them. Second, the Standard Model cannot explain dark matter. When astronomers observe the motions of galaxies, they find something deeply puzzling. Galaxies rotate too fast. Based on the amount of visible matter they contain, their outer stars should fly off into space, like mud flying off a spinning wheel. But they do not. Something invisible is holding them together. That something has been named dark matter, and it accounts for approximately 27% of the total mass-energy content of the universe. That is more than 5 times the amount of ordinary matter, the stuff that makes up every star, every planet, every person, everything you have ever seen or touched. And yet the Standard Model has no particle that could be dark matter. None of its 17 fundamental particles fit the bill. Third, there is dark energy. In 1998, astronomers discovered something even more puzzling than dark matter. The expansion of the universe is not slowing down, as everyone expected. It is speeding up. Something is pushing the fabric of space apart, accelerating the expansion against the pull of gravity. That something has been called dark energy, and it accounts for approximately 68% of the total mass energy content of the universe. Combined with the dark matter, this means that the Standard Model describes at most 5% of the universe. 5%. We have built the most successful theory in the history of science, and it describes only 1/20th of what actually exists. Fourth, there is the matter-antimatter asymmetry. When the Big Bang occurred, it should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other, converting entirely into energy. If equal amounts were created, they should have wiped each other out completely, leaving a universe filled with nothing but radiation, no atoms, no stars, no life. But here we are. Somehow, there was a tiny excess of matter over antimatter, roughly 1 part in a billion, and that tiny excess is everything we see around us. The Standard Model can account for some matter-antimatter asymmetry through a phenomenon called CP violation, but the amount it predicts is nowhere near enough to explain the universe we observe. There must be additional sources of CP violation that we have not yet discovered. Fifth, there is the hierarchy problem. The Higgs boson has a mass of 125 gigaelectron volts. That sounds like a lot, but in the context of particle physics, it is remarkably light. Quantum corrections from virtual particles should drive the Higgs mass up to the Planck scale, around 10 to the 19th gigaelectron volts, which is roughly 10 quadrillion times heavier than what we observe. For the Higgs mass to come out as low as it does, there must be an extraordinarily precise cancellation between different quantum contributions, fine-tuned to roughly 1 part in 10 to the 34th. This level of fine-tuning is deeply uncomfortable for physicists. It feels like there should be some mechanism, some deeper principle that explains why the Higgs mass is what it is. But the Standard Model offers no such explanation. So here is where we stand. The Standard Model is a masterpiece. It predicts the outcomes of experiments with extraordinary precision, sometimes to more than 10 decimal places. It has been tested and confirmed thousands of times. It is, without exaggeration, the crowning achievement of human intellect. And yet, it is also clearly, demonstrably incomplete. It is like a map that covers 5% of the territory and leaves the rest blank. It is like a book that tells a beautiful story but is missing 95% of its pages. This is why CERN exists. This is why the LHC was built. Not just to confirm the Standard Model, but to break it, to find the cracks, to discover what lies beyond. And the cracks, as I'm about to show you, have finally begun to appear. Let us talk about anomalies. In the language of physics, an anomaly is a measurement that does not match the prediction of the Standard Model. It is a data point that sticks out, a result that makes physicists furrow their brows and say, "Wait, that is not right." Anomalies are the lifeblood of scientific progress, because every major revolution in physics began with someone noticing that the data did not quite fit the theory. Newton's laws worked beautifully until someone noticed that Mercury's orbit was slightly off. That anomaly eventually led to Einstein's general relativity. And now, a collection of anomalies emerging from CERN and related experiments is pointing toward what could be the next great revolution. The first anomaly I want to tell you about is one of the most fascinating measurements in all of physics. It involves a particle called the muon, and a property called its magnetic moment. The muon is essentially a heavier version of the electron. It has the same electric charge, the same spin, but it is about 207 times more massive. And like all charged particles with spin, the muon behaves like a tiny magnet. The strength of this magnet is characterized by a number called the G factor. In classical physics, the Dirac equation predicts that the G factor of the muon should be exactly 2. But we do not live in a purely classical universe. We live in a quantum universe where the vacuum of space is not empty, but is a seething, boiling foam of virtual particles constantly popping into and out of existence. These virtual particles interact with the muon, slightly altering its magnetic properties. The result is that the G factor is not exactly 2, but slightly more than 2. The difference, called the anomalous magnetic moment, or G-2, is incredibly small but measurable. The beauty of this measurement is that every particle in the Standard Model contributes to it. Every force, every interaction, every virtual particle leaves its fingerprint on the muon's magnetic moment. This means that if there are particles we do not know about, hidden particles beyond the Standard Model, they too would contribute. The muon's magnetic moment is like a window into the invisible. It is sensitive to everything that exists, even things we cannot directly detect. For decades, there has been a tantalizing discrepancy between the measured value of the muon's G-2 and the theoretical prediction. The original measurements came from Brookhaven National Laboratory in the late 1990s and early 2000s. They found a value that was slightly higher than what the Standard Model predicted. The discrepancy was around 3.7 sigma, not quite enough to claim a discovery, which requires 5 sigma, but enough to make the physics world sit up and take notice. Then came the Fermilab muon G-2 experiment. In 2013, the massive storage ring from Brookhaven was transported across the country to Fermilab in Illinois. After years of upgrades and improvements, the experiment began collecting data in 2017. In 2021, they released their first results, confirming the Brookhaven measurement with improved precision. The discrepancy held. The physics world buzzed with excitement. But here is where the story takes an unexpected turn. In June 2025, Fermilab released its final results. The measurement achieved an extraordinary precision of 127 parts per billion, surpassing the experiment's design precision of 140 parts per billion and improving upon the Brookhaven result by a factor of 4. The final experimental value was exquisitely precise. But in the meantime, something had changed on the theoretical side. The theoretical prediction of the muons G-2 is extremely difficult to calculate. The dominant source of uncertainty comes from something called hadronic vacuum polarization, a process where the virtual photon interacting with the muon briefly transforms into a cloud of quarks and gluons that is incredibly hard to model. For years, theorists used a data-driven approach, relying on measurements from electron-positron colliders to estimate this contribution. This was the basis of the 2020 white paper from the muon G-2 theory initiative, which reported a prediction that showed a significant discrepancy with the experimental measurement. But then, lattice QCD, a computational technique that calculates quantum chromodynamics from first principles using a grid-like approximation of spacetime, made rapid progress. The lattice QCD calculations gave a different answer for the hadronic vacuum polarization contribution, one that shifted the theoretical prediction significantly closer to the experimental measurement. In May 2025, the Theory Initiative published an updated prediction based on these lattice QCD calculations, and the discrepancy with the experimental measurement was dramatically reduced. So, does this mean the anomaly is dead? Not at all, and here is why this story is actually more interesting, not less. The fact that two different theoretical methods, the data-driven approach and lattice QCD, give significantly different answers for the same quantity means that something is not understood. There is a tension within the theory itself. Either the data-driven method has a problem, or the lattice QCD calculations are missing something, or there is genuinely new physics lurking in the hadronic sector that is showing up differently in the two approaches. As Ada El-Qadra, chair of the Theory Initiative, has stated, regardless of the outcome of the comparison between lattice QCD and the data-driven method, the resolution will yield profound insights. The puzzle is not solved. It has merely transformed into a deeper puzzle. And there is something else. Even if the muon G-2 anomaly turns out to be fully explained by the standard model, the techniques and precision developed in the process have created an extraordinary tool for probing new physics. The next-generation experiment at J-Park in Japan, scheduled to begin data taking in 2030, will use an entirely different experimental technique to push the precision even further, and it will also search for the electric dipole moment of the muon, a quantity that the standard model predicts should be essentially zero. If a non-zero electric dipole moment is found, it would be an unambiguous signal of physics beyond the standard model. The hunt is far from over. The second major anomaly involves the mass of the W boson. The W boson is one of the carriers of the weak nuclear force, responsible for the type of radioactive decay that powers the sun and drives the synthesis of elements in stellar cores. Its mass is one of the most precisely predicted quantities in the standard model. All the parameters of the theory, including the masses of the top quark, the Higgs boson, and the Z boson, constrain the W boson mass through quantum loop corrections. The standard model predicts it should be approximately 80,357 mega-electron-volts, give or take about 6. In April 2022, the CDF experiment at Fermilab dropped a bombshell. After a decade of painstaking analysis, they announced a measurement of the W boson mass that was 80,433.5 megaelectronvolts. This was roughly 80 megaelectronvolts higher than the standard model prediction, a discrepancy of 7 standard deviations. 7 sigma is enormous. In particle physics, 5 sigma is considered a discovery. 7 sigma suggests that either something is dramatically wrong with our understanding of the universe, or something is dramatically wrong with the measurement. The physics world erupted. If the CDF result was correct, it would mean the standard model was fundamentally flawed in a way that no one had anticipated. New particles, new forces, new physics would be required to explain the discrepancy. Papers poured in by the hundreds, proposing every conceivable explanation, from supersymmetry to extra dimensions to exotic Higgs sectors. But then the counterweights arrived. The ATLAS experiment at CERN had already measured the W boson mass with their own data, and their result was consistent with the standard model. And in September 2024, the CMS experiment at CERN released its own measurement, based on over 100 million W bosons reconstructed from LHC data. Their result was 80,360.2 megaelectronvolts, give or take about 10, which was fully consistent with the standard model prediction and in significant tension with the CDF result. So what happened? Most physicists now believe that the CDF measurement likely suffered from an unidentified systematic error, perhaps related to the modeling of the W boson production process or the calibration of the detector. But the story illustrates something important. It shows that our theories are balanced on a knife edge. A shift of even 80 megaelectronvolts out of 80,000, a difference of roughly 0.1%, would blow the standard model wide open. The fact that nature is consistent with the standard model to this level of precision is remarkable. But it also means that the hidden layer, if it exists, is hiding very effectively. It is whispering, not shouting, and we need extraordinarily sensitive ears to hear it. The third set of anomalies comes from a domain of physics called flavor physics, studied in exquisite detail by the LHCb experiment at CERN. Flavor physics is concerned with the transformations that particles undergo, particularly the decays of particles containing heavy quarks. One of the most exciting areas has been the study of B-mesons, composite particles containing a bottom quark. One of the foundational assumptions of the standard model is something called lepton universality. This means that the 3 generations of leptons, electrons, muons, and taus should interact with the weak force in exactly the same way. The only differences between them should be due to their different masses. If you adjust for mass, the rate at which a B-meson decays into final states involving electrons versus muons should be identical. Starting around 2014, the LHCb experiment began finding hints that this was not the case. A series of measurements suggested that B-mesons were decaying into muons slightly less often than into electrons, violating lepton universality. The deviations were not large enough to claim a discovery, typically in the range of 2 to 3 sigma, but they were consistent across multiple measurements and multiple decay channels. The pattern was suggestive of a new force or a new particle, perhaps a leptoquark or a heavy Z-prime boson that coupled differently to different generations of leptons. However, with more data and improved analysis techniques, the picture became more complex. Some of the most striking anomalies decreased in significance. The latest LHCb results have brought several of these measurements closer to the standard model predictions. But the story is not over. Some measurements remain intriguing. The upgraded LHCb detector, now collecting data with significantly improved capabilities during Run 3, is generating an unprecedented volume of precision data. And the LHCb collaboration has discovered something remarkable in the process, an entirely new zoo of exotic particles that were never predicted by the quark model. Let me tell you about these exotic particles because they are genuinely mind-blowing. For decades, the conventional understanding was that quarks combine in only two ways. Three quarks bound together form a baryon, like a proton or a neutron. A quark and an antiquark bound together form a meson, like a pion or a kaon. These are the familiar inhabitants of the subatomic world, neatly catalogued in textbook after textbook. But the theory of the strong force, quantum chromodynamics, actually allows for more exotic combinations. 4 quarks bound together would form a tetraquark. 5 quarks would form a pentaquark, and LHCb has found them. As of the latest count, 24 new exotic hadrons have been discovered at the LHC, including multiple tetraquarks and pentaquarks. These particles were theoretical curiosities for decades, dismissed by many physicists as unlikely to exist in nature. And yet, there they are, appearing in the data with undeniable statistical significance. The existence of these exotic particles does not directly prove the existence of a hidden layer beneath reality, but it tells us something profound. It tells us that even within the standard model, there are structures and configurations that we did not expect. The subatomic world is richer, more complex, and more surprising than our textbooks suggested. If we were wrong about what combinations of quarks are possible, what else might we be wrong about? What other surprises are waiting to be found? Now, let us talk about what might be the most compelling hint of all. In 2025, CERN scientists published a remarkable study about the hidden order inside particle chaos. When protons collide at the LHC, the result looks like absolute chaos. Hundreds of particles flying in every direction, an explosion of subatomic debris that seems utterly random. But when physicists from the Institute of Nuclear Physics of the Polish Academy of Sciences analyzed the entropy, the measure of disorder, of these collisions, they found something unexpected. They found that the entropy of the particles emerging from the collision was the same as the entropy of the quarks and gluons in the initial chaotic phase. This might not sound surprising at first, but think about it more carefully. In the initial moments after the collision, you have a boiling sea of quarks and gluons, including short-lived virtual particles, interacting in an incredibly complex web. It looks like it should be far more disordered than the neat hadrons that eventually emerge. And yet the entropy is preserved. This preservation of entropy is a consequence of a fundamental principle of quantum mechanics called unitarity. Unitarity means that the total probability of all possible outcomes must equal 1, and that quantum processes must be, in principle, reversible. Information cannot be created or destroyed. It is one thing to know this as a mathematical principle. It is quite another to see it confirmed in the violent, extreme conditions of a proton collision at 13 tera-electronvolts. As Professor Krzysztof Kutak, who led the study, noted, it is one thing to deal with a theory that exhibits unitarity at the level of quarks and gluons, and quite another to observe it in real data on produced hadrons. This result confirms that even in the most chaotic processes we can create, there is a hidden order. The information is preserved, the structure is maintained. Reality has a coherence that persists even through the most extreme transformations. And this hidden order, this preservation of information through chaos, is itself a kind of hidden layer. It is a structure beneath the apparent randomness, a pattern beneath the noise. But the hidden layers go much deeper than this. Let me take you into the realm that physicist Harry Cliff, who works on the LHCb experiment, and theoretical physicist Andrei Buras from the Technical University of Munich have been exploring. They call it the zeptouniverse. To understand the zeptouniverse, you need to understand the concept of resolution in particle physics. Just as a microscope allows you to see smaller and smaller structures by using shorter and shorter wavelengths of light, a particle collider allows you to probe smaller and smaller distance scales by using higher and higher energies. The relationship between energy and distance in quantum mechanics means that higher energy corresponds to shorter distances. The LHC, operating at 13 tera-electron volts, can directly probe distances down to about 50 zeptometers. A zeptometer is 10 to the minus 21 meters, or 1/60th of a meter. This is already extraordinarily small, roughly 100 million times smaller than an atom. But Buras argues that the really interesting physics might be hiding at even shorter distances, around 10 to the minus 21 meters or below. This is the zeptouniverse, a realm where new particles, new forces, and new physics could be lurking, just beyond the direct reach of the LHC. The energy required to directly probe this scale would be around 200 tera-electron volts, roughly 15 times higher than what the LHC can achieve. No current or planned collider can reach this energy directly. But here is the brilliance of Buras's approach. You do not always need to smash particles together at higher energies to see the effects of heavy new particles. There is another way. It is indirect, subtle, and requires extraordinary precision, but it works. The idea is to look at extremely rare particle decays, processes that are so unlikely in the standard model that even a tiny contribution from new physics would be noticeable. Buras identified 7 such processes, which he calls the Magnificent Seven. All 7 involve extremely rare decays of particles containing strange or bottom quarks. These decays are like echoes from the zeptouniverse, faint signals that carry information about physics at energy scales we cannot directly reach, and experiments are already searching for them. One example involves the decay of a B meson into a kohan and 2 neutrinos. In 2023, the Bell 2 experiment in Japan observed this decay for the first time. Another example involves the decay of a positively charged kaon into a pion and a neutrino-antineutrino pair. In September 2024, the NA62 experiment at CERN measured this ultra-rare decay, finding that less than 1 in 10 billion kaons decays in this way. Because these interactions are extraordinarily sensitive to deviations from the standard model, they serve as powerful probes of new physics that might be hiding in the zeptouniverse. This is a critical point that I want you to understand deeply. The hidden layer beneath reality might not be something dramatic and obvious. It might not announce itself with a blaring signal that is impossible to miss. Instead, it might reveal itself through whispers, through the tiniest deviations in the rarest processes, detectable only with the most precise measurements humanity has ever made. The zeptouniverse is not a place you can visit. It is not a place you can see. It is a realm of reality that exists at scales so small that the only way to explore it is through the mathematical language of quantum field theory and the almost impossibly precise experiments that test that language. Now, let us broaden our perspective and talk about the hidden layer in its grandest form, because the anomalies in the zeptouniverse are really just pieces of a much larger puzzle. The puzzle of what lies beneath the visible universe. And to appreciate the full scope of this puzzle, we need to talk about the 2 greatest mysteries in all of cosmology, dark matter and dark energy. Dark matter was first proposed in the 1930s by the Swiss astronomer Fritz Zwicky. He was studying galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, and he found that they were moving too fast. The galaxies at the edges of the clusters were orbiting so quickly that they should have been flung out into space long ago. The only way to explain their motion was if there was far more mass in the cluster than what was visible. Zwicky called this missing mass dunkle materie, dark matter. For decades, Zwicky's idea was largely ignored. But in the 1970s, the American astronomer Vera Rubin and her colleague Kent Ford provided the evidence that could not be denied. They measured the rotation curves of individual galaxies and found the same pattern that Zwicky had seen in clusters. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center, instead of slower as Newton's laws predicted. The only explanation was an enormous halo of invisible mass surrounding each galaxy, extending far beyond the visible stars and gas. Since then, the evidence for dark matter has become overwhelming. Gravitational lensing, the bending of light from distant objects by the gravity of foreground mass, has revealed the presence of massive invisible structures in the universe. The cosmic microwave background radiation, the afterglow of the Big Bang, contains a pattern of fluctuations that can only be explained if dark matter was present in the early universe, providing the gravitational scaffolding around which ordinary matter later condensed to form galaxies. Computer simulations of cosmic structure formation reproduce the observed web of galaxies only when dark matter is included. We know dark matter exists. We know it accounts for about 27% of the universe's total mass energy content. We know it does not interact with light, which is why it is invisible. We know it interacts through gravity, which is how we detected it in the first place. And we know it is not any of the 17 particles in the Standard Model. So, what is it? This is one of the biggest open questions in science. There are many candidates. Weakly interacting massive particles, or WIMPs, were the leading candidate for decades. These hypothetical particles would interact with ordinary matter through the weak nuclear force, making them detectable, in principle, in sensitive underground experiments. The LHC has searched extensively for WIMPs, looking for events where a collision produces a pair of invisible particles that carry away energy, leaving a characteristic missing energy signature. But so far, no WIMPs have been found. The parameter space for WIMPs has been dramatically narrowed, and while they have not been entirely ruled out, the absence of discovery has shifted attention to other candidates. Axions are another possibility. Originally proposed to solve a different problem in quantum chromodynamics, axions would be extremely light and extremely weakly interacting. They would be incredibly difficult to detect, but several experiments around the world are now searching for them using innovative techniques based on the conversion of axions into photons in strong magnetic fields. Sterile neutrinos, dark photons, and other exotic particles have also been proposed. And this is where CERN's newest experiments become particularly exciting. The Phaser experiment, which stands for Forward Search Experiment, was installed at the LHC in 2018 and began collecting data during Run 3. It sits 480 meters downstream from the Atlas collision point, in a side tunnel, where it is designed to catch long-lived particles that are produced in collisions but travel a significant distance before decaying. These are exactly the kind of particles that could serve as messengers from a dark sector, a parallel world of particles and forces that overlaps with our own, but interacts with it only very weakly. Phaser has already produced its first physics results, including the detection of neutrinos produced in LHC collisions, a feat that had never been achieved before. While it has not yet found dark sector particles, the experiment is still in its early stages, and its sensitivity will increase dramatically with more data. The concept behind Phaser represents a profound shift in how we search for new physics. Instead of looking for heavy particles produced directly in collisions, we look for light, weakly interacting particles that slip through our main detectors unnoticed, and reveal themselves only far downstream. It is the physics equivalent of looking for a ghost, not by confronting it directly, but by setting a trap in the hallway where it might pass. Beyond FACER, there are proposals for even more ambitious experiments designed to search for dark sector particles. Mathusla, a proposed surface-level detector above the Atlas collision point, would look for ultra-long-lived particles that travel upward through 100 meters of rock before decaying. SHIP, the search for hidden particles, is a proposed beam dump experiment that would use CERN's superproton synchrotron to produce and detect feebly interacting particles. These experiments embody a new philosophy in particle physics, the recognition that the hidden layer might not be heavy and hard to produce, but instead light and hard to detect, hiding in plain sight because it interacts so weakly with ordinary matter. And there is a theoretical framework that ties all of this together. It is called the Hidden Valley Model, developed by physicist Matt Strassler and others. In this picture, there exists an entirely parallel sector of particles and forces, separated from our visible sector not by a physical barrier, but by the weakness of the interactions connecting them. Imagine two valleys separated by a high mountain range. In one valley, you have the standard model, with all its familiar particles and forces. In the other valley, you have the hidden sector, with its own particles, its own forces, its own internal dynamics, completely invisible to us. The only way particles can cross from one valley to the other is through rare quantum processes, tunneling through the mountain, as it were. The Hidden Valley model predicts that when standard model particles collide at high enough energies, they can occasionally produce particles from the hidden sector. These particles would be invisible to our detectors. But when they decay back into standard model particles, they could produce distinctive experimental signatures, such as displaced vertices, where particles appear to originate from a point away from the collision, or anomalous patterns of missing energy. This is not just speculation. This is a well-defined theoretical framework with specific, testable predictions. And CERN is testing them. Now, let me take you even deeper, because the hidden layer beneath reality might not just be new particles and forces. It might be something far more radical. It might be entirely new dimensions of space. The idea that our universe has more than 3 spatial dimensions is not new. It goes back to 1921, when the German mathematician Theodor Kaluza showed that by adding a single extra spatial dimension to Einstein's general relativity, the equations of electromagnetism emerged naturally. In other words, what we experience as the electromagnetic force might actually be gravity, but gravity propagating through a dimension we cannot see. In 1926, the Swedish physicist Oskar Klein refined Kaluza's idea by suggesting that the extra dimension was compactified, curled up into a tiny circle so small that it would be invisible at everyday scales. For decades, Kaluza-Klein theory was a mathematical curiosity. Interesting, but not taken too seriously. Then came string theory. In the 1980s and 1990s, string theory emerged as a leading candidate for a theory of quantum gravity, a framework that could, in principle, unify all the forces of nature, including gravity, into a single mathematical structure. But string theory made an extraordinary demand. For the mathematics to be consistent, spacetime must have not 4 dimensions but 10. In the most general version, M theory, it requires 11. Where are these extra dimensions? The standard answer is the same one Klein proposed in 1926. They are compactified, curled up at scales so small that we cannot detect them. The shape and size of these extra dimensions determine the properties of the particles and forces we observe in our 4-dimensional world. Different configurations of the extra dimensions give rise to different physics, different particle masses, different force strengths, different numbers of particle generations, The landscape of possible configurations is estimated to be roughly 10 to the 500, a number so vast that it defies comprehension. But there is another possibility, one that is particularly relevant to the search for hidden layers at CERN. In 1998, Lisa Randall and Raman Sundram proposed a radical alternative. Instead of the extra dimensions being tiny and curled up, they could be large or even infinite, as long as they are warped. In the Randall-Sundram model, our visible universe is a four-dimensional brane, a membrane-like object embedded in a higher dimensional space called the bulk. Gravity, unlike the other forces, can propagate through the bulk, which is why it appears so much weaker than the other forces. The gravitational force we feel is just the pale shadow of gravity in the higher dimensional bulk, diluted by the geometry of the extra dimension. This model makes a testable prediction. If extra dimensions exist and are accessible at LHC energies, they would produce signatures in the data. Gravitons, the hypothetical carriers of gravity, could escape into the extra dimensions, showing up as missing energy in collisions. Heavy Kaluza-Klein partner particles, heavier versions of known particles that carry momentum in the extra dimensions, could be produced and detected. In the most exotic scenario, microscopic black holes could form when two particles collide with enough energy in the higher dimensional space. These micro-black holes would be harmless, evaporating almost instantly through Hawking radiation, but their decay products would be spectacular and unmistakable. CERN has searched for all of these signatures: extra-dimensional gravitons, Kaluza-Klein particles, micro-black holes. So far, none have been found. But this does not mean extra dimensions do not exist. It means that if they exist, they are either at energy scales beyond the LHC's reach, or they manifest in ways we have not yet thought to look for. The search continues, and the high luminosity LHC, which will begin operating in 2030 after 4 years of upgrades starting this summer, will provide dramatically more data to work with. And this brings me to one of the most radical ideas in all of modern physics, an idea that might represent the deepest hidden layer of all. The idea that space-time itself is not fundamental, that the very fabric of reality, the stage on which everything happens, is not the foundation but the surface. That space and time are emergent properties, arising from something deeper, something we have not yet identified. This idea has multiple origins. One comes from black hole physics. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of the amount of information they contain. And remarkably, this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This was profoundly puzzling. In every other system in physics, entropy is proportional to volume. If you have a box of gas, doubling the volume doubles the entropy. But for a black hole, the information content is stored on the surface, not in the interior. This led to the holographic principle, proposed by Gerard 't Hooft and later refined by Leonard Susskind. The holographic principle states that all the information contained within a region of space can be described by a theory living on the boundary of that region. The three-dimensional universe might be, in some deep sense, a holographic projection of information encoded on a two-dimensional surface. In 1997, Juan Maldacena provided a concrete realization of this idea in the context of string theory. He showed that a theory of gravity in a particular five-dimensional spacetime, called anti-de Sitter space, is mathematically equivalent to a theory without gravity on the four-dimensional boundary of that space. This duality, known as the ADS/CFT correspondence, has become one of the most important theoretical tools in physics. It suggests that gravity, and by extension, space-time itself, might be emergent, arising from the quantum entanglement of degrees of freedom in a lower dimensional theory. And here's where it gets really wild. In 2013, Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture. ER refers to Einstein-Rosen bridges, which are wormholes connecting distant regions of spacetime. EPR refers to Einstein-Podolsky-Rosen entanglement, the quantum mechanical phenomenon where two particles can be correlated in such a way that measuring one instantaneously affects the other, regardless of the distance between them. Maldacena and Susskind proposed that these two seemingly unrelated phenomena are actually the same thing. Every pair of entangled particles is connected by a microscopic wormhole. And if this is true, then the fabric of spacetime, the very geometry of the universe, is woven from quantum entanglement. Think about what this means. If ER equals EPR is correct, then space itself is not fundamental. It is not the stage, it is the play. It emerges from the relationships between quantum systems. The hidden layer beneath reality is not a new set of particles or a new force or a new dimension. It is the quantum information itself, the pattern of entanglement from which everything, space, time, matter, energy, everything we experience, crystallizes into existence. CERN cannot directly test this idea, at least not yet. The energies involved are the Planck energy, roughly 10 to the 19th gigaelectron volts, which is about a quadrillion times higher than the LHC can achieve. But here's the connection. Every anomaly that CERN finds, every deviation from the standard model, every unexpected result, is a clue about the deeper structure of reality. If the standard model is just an effective theory, an approximation of something deeper, then the anomalies are the seams where the approximation breaks down. And those seams point downward, toward the hidden layer, toward whatever reality is actually made of at its most fundamental level. Let me now take you through the specific experiments at CERN in more detail, because the story of the hidden layer is ultimately a story told by these extraordinary machines and the people who built and operate them. The ATLAS detector is a marvel of engineering. It is 46 meters long, 25 meters in diameter, and weighs 7,000 tons. It is the largest particle detector ever built. Its name stands for a toroidal LHC apparatus, and it is designed to be a general-purpose detector capable of studying virtually any phenomenon that might emerge from proton-proton collisions. At the heart of ATLAS is the inner detector, a tracking system that records the paths of charged particles as they spiral through a magnetic field. Surrounding this is the calorimeter system, which measures the energy of particles by absorbing them. And surrounding everything is the muon spectrometer, a system of chambers that detects muons, the only charged particles that penetrate through the entire detector. ATLAS was one of the two experiments that discovered the Higgs boson in 2012, and it has been at the forefront of the search for new physics ever since. It has searched for supersymmetric particles, extra dimensions, dark matter, heavy resonances, and dozens of other exotic signatures. And while it has not yet found definitive evidence of new physics, its measurements of the Higgs boson's properties are becoming increasingly precise, creating an ever tighter web of constraints that any theory of physics beyond the standard model must satisfy. One of the most important things ATLAS is doing right now is measuring the Higgs boson's properties with extraordinary precision. The Higgs boson interacts with other particles in proportion to their mass. By measuring these interactions precisely, physicists can check whether the Higgs boson behaves exactly as the standard model predicts. Any deviation, even a small one, would be evidence of new physics. It could mean that the Higgs boson is not a fundamental particle but a composite, made of smaller constituents we have not yet discovered. it could mean that there are additional Higgs bosons, predicted by many theories of physics beyond the Standard Model. Or it could mean that the Higgs boson interacts with particles from a hidden sector, altering its behavior in subtle ways. The CMS detector, which sits at the opposite side of the LHC ring from ATLAS, is its complement and rival. CMS stands for Compact Moon Solenoid, though at 15 meters in diameter, 21 meters in length, and 14,000 tons in weight, compact is a relative term. While ATLAS uses a toroidal magnet system, CMS uses a solenoid magnet, the most powerful solenoid ever built, generating a field of 4 teslas. This different design philosophy means that while ATLAS and CMS measure the same physics, they do so in different ways, providing independent verification of each other's results. It was CMS that provided the crucial measurement of the W boson mass that helped resolve the CDF anomaly, and CMS continues to search for new physics in every channel imaginable. Its searches for dark matter, for exotic resonances, for long-lived particles, and for deviations in Higgs boson couplings are all pushing the boundaries of what we know. The LHCb experiment takes a different approach entirely. While ATLAS and CMS are general-purpose detectors that surround the entire collision point, LHCb is a forward spectrometer, designed to capture particles that fly off in a specific direction. This makes it ideally suited for studying the decays of B mesons and other particles containing heavy quarks, which tend to be produced at small angles. LHCb has been one of the most scientifically productive experiments at the LHC. It has made world-leading measurements of CP violation, the asymmetry between matter and antimatter in particle decays. It has discovered a remarkable collection of exotic hadrons, including pentaquarks and tetraquarks, and its measurements of rare B meson decays have provided some of the most sensitive tests of the Standard Model's predictions for flavor physics. For Run 3, the LHCb detector underwent a major upgrade, replacing its hardware trigger with a fully software-based real-time analysis system. This means that every single collision is analyzed by algorithms running on a massive computing farm, allowing the experiment to capture far more rare decays than before. The data collected during Run 3 will be the most precise flavor physics dataset ever assembled, and it will provide the definitive word on many of the anomalies that have tantalized physicists for the past decade. The ALICE experiment is perhaps the most exotic of the 4 main LHC detectors. Its purpose is not to search for new particles in the traditional sense, but to recreate and study a state of matter that existed in the first few microseconds after the Big Bang, the quark-gluon plasma. Under normal conditions, quarks are always confined inside hadrons, bound together by the strong force. You can never see a free quark, but at extreme temperatures, around 5.5 trillion degrees Celsius, the strong force weakens, and the quarks and gluons are liberated, forming a primordial soup of deconfined matter. This is the quark-gluon plasma, and ALICE creates it by colliding beams of heavy ions, such as lead nuclei at the LHC. The quark-gluon plasma is fascinating, because it is the closest thing we can create to the conditions that existed at the very beginning of the universe. By studying its properties, we learn about the fundamental nature of the strong force, about the phase transitions that matter underwent as the early universe cooled, and about the emergence of structure from the primordial fireball. And in 2025, ALICE achieved something that would have seemed like alchemy. The experiment detected the conversion of lead nuclei into gold nuclei during heavy ion collisions at the LHC. This is not the philosopher's stone of medieval legend. The gold nuclei are produced in fleeting quantities and exist for only about a microsecond before decaying. But the fact that nuclear transmutation, The ancient dream of the alchemists has been achieved at a particle collider is a testament to the extraordinary capabilities of these machines. The ALICE collaboration calculated that the LHC produces about 89,000 gold nuclei per second during lead-ion collisions. Of course, these nuclei are traveling at nearly the speed of light and exist for the briefest of instants, so no one is going to get rich from this process. But the physics is real and beautiful. When two lead nuclei pass close to each other without directly colliding, the intense electromagnetic fields they carry can knock protons out of one nucleus, converting it from lead, with 82 protons, to gold, with 79 protons. It is nuclear physics at its most elegant. There is another CERN experiment I want to tell you about, one that directly probes the hidden layer through the study of antimatter. The BASE experiment, which stands for Baryon-Antibaryon Symmetry Experiment, operates at CERN's Antimatter Factory, a unique facility that produces and stores antiprotons for precision measurements. In July 2025, the BASE collaboration achieved a remarkable breakthrough. They demonstrated the first antimatter quantum bit, or qubit. By trapping a single antiproton in a magnetic field and maintaining extraordinary control over its quantum state, they were able to hold the antiproton spin in a quantum superposition, a state where it is simultaneously spin up and spin down for approximately 50 seconds. This is the fundamental operation of a qubit, the basic unit of quantum information processing. Now, no one is going to build a quantum computer out of antiprotons anytime soon. The purpose of this achievement is far more profound. By creating an antimatter qubit, physicists can make incredibly precise comparisons between the properties of matter and antimatter. If there is any difference at all between how matter and antimatter behave at the quantum level, this technique could reveal it. And any such difference would be a direct window into the matter-antimatter asymmetry that allowed our universe to exist, a direct probe of the hidden layer of physics beyond the standard model. Also, in 2025, the ALPHA experiment at CERN's Antimatter Factory achieved a breakthrough in antimatter production. A new cooling technique allowed the experiment to produce antihydrogen atoms, the antimatter counterpart of ordinary hydrogen, 8 times faster than before. Antihydrogen consists of an antiproton orbited by a positron, and by studying its properties in exquisite detail, comparing them to the properties of ordinary hydrogen, physicists can test whether the laws of physics are truly symmetric between matter and antimatter. These antimatter experiments are searching for the hidden layer in a different way than the high-energy collisions at the LHC. They are looking not for new particles produced at extreme energies, but for tiny asymmetries in the behavior of known particles, asymmetries that would reveal the existence of new physics. It is the difference between smashing through a wall to see what is on the other side and running your fingers over the surface of the wall, feeling for the seams, looking for the cracks. Now, I want to take a step back and talk about what all of this means in the broadest possible context. Because the search for the hidden layer is not just a technical exercise in particle physics. It is a deeply human endeavor. It is the latest chapter in a story that began when the first human looked up at the night sky and asked, "What is all of this?" Every civilization throughout history has grappled with this question. And every civilization has constructed an answer, a model of reality that seemed complete and satisfying, until someone pushed deeper and found that the model was just the surface of something more profound. The ancient Greeks believed that everything was made of 4 elements: earth, water, air, and fire. This model seemed to explain everything they could observe. But when chemistry emerged in the 18th and 19th centuries, the 4 elements were replaced by the periodic table, a system of over 90 naturally occurring elements, each with its own unique properties. Then, in the late 19th century, physicists discovered that atoms were not indivisible, as their name implied, but were composed of smaller particles, protons, neutrons, and electrons. This was a hidden layer beneath the chemical elements. The periodic table, which had seemed like the fundamental truth, was actually a surface pattern emerging from the deeper structure of atomic physics. Then, in the 1960s and 1970s, physicists discovered that protons and neutrons were themselves not fundamental, but were composed of quarks. Another hidden layer, another level of depth beneath what had seemed like bedrock. At each stage, the discovery of a new layer did not invalidate the previous understanding. Chemistry still works. Atomic physics still works. But each discovery revealed that what we thought was the bottom was actually just another floor, with more structure underneath. And now we stand at the edge of what might be the deepest layer yet. The Standard Model describes the quarks, the leptons, the bosons, the Higgs field. It accounts for 3 of the 4 fundamental forces. It explains the visible universe with breathtaking precision, but it describes only 5% of the total mass energy content of the cosmos. It does not include gravity. It does not explain why its 17 particles have the masses they do. It does not explain the matter-antimatter asymmetry that allowed us to exist. It is, in the most literal sense, a surface-level description. What lies beneath? This is the question. And CERN, with all its extraordinary machines and brilliant minds, is humanity's best attempt at an answer. Let me tell you about supersymmetry, because the story of Susie, as physicists call it, is both the most beautiful and the most heartbreaking story in modern physics. Supersymmetry is a theoretical framework that proposes a profound connection between the 2 broad categories of particles in nature, bosons and fermions. Bosons are force carriers, particles with integer spin, like the photon and the gluon. Fermions are matter particles, particles with half-integer spin, like the electron and the quark. In the Standard Model, these 2 categories are completely separate, related by no known symmetry. But supersymmetry proposes that for every boson, there exists a fermionic superpartner, and for every fermion, there exists a bosonic superpartner. Electrons would have selectrons. Quarks would have squarks. Photons would have photinos. The Higgs boson would have a Higgsino. If supersymmetry exists, it would solve several of the Standard Model's biggest problems simultaneously. It would solve the hierarchy problem by providing a natural mechanism for canceling the quantum corrections that drive the Higgs mass toward the Planck scale. It would provide a natural candidate for dark matter in the form of the lightest supersymmetric particle, typically the neutralino, which would be stable, electrically neutral, and weakly interacting, exactly the properties needed for dark matter. And it would allow the 3 non-gravitational forces to unify at a single energy scale, something that does not quite work in the Standard Model alone, but happens naturally in its supersymmetric extension. Supersymmetry is mathematically beautiful. It is the only way to extend the symmetry group of spacetime, the Poincare group, in a non-trivial way, as proven by the Coleman-Mandela theorem and its supersymmetric extension, the Hague-Lopushansky-Sonius theorem. It is a necessary ingredient of string theory, and for decades it was the leading candidate for physics beyond the Standard Model. The LHC was supposed to find it. It did not. Run after run, search after search, the LHC experiments have looked for supersymmetric particles and found nothing. The parameter space for the simplest supersymmetric models has been dramatically reduced. The superpartners, if they exist, must be much heavier than originally expected, which undermines some of the theoretical motivations for supersymmetry in the first place. If the superpartners are too heavy, they cannot solve the hierarchy problem without introducing a new fine-tuning problem. For thousands of physicists who spent their careers developing and testing supersymmetric theories, this has been a profoundly difficult time. The emotional investment is enormous. The intellectual investment is staggering. Decades of work, thousands of papers, entire careers built on the expectation that supersymmetry would be discovered at the LHC, and it was not. Is supersymmetry dead? The honest answer is no, not completely. There are more complex versions of supersymmetry, split SUSY, natural SUSY, stealth SUSY, that can hide the superpartners at higher masses while still solving some of the theoretical problems. And the high luminosity LHC and future colliders will continue to search. But the simplest, most natural versions of supersymmetry are now severely constrained. If SUSY exists, it is not the simple, elegant picture that physicists hoped for. It is something more complex, more hidden, more subtle. And this raises a profound question. If supersymmetry is not the answer, what is? What else could solve the hierarchy problem? What else could explain dark matter? What else could provide the missing link between quantum mechanics and gravity? The answer might be something we have not even thought of yet. The hidden layer might be structured in ways that our current theoretical frameworks cannot even describe. This is why the anomalies are so important. This is why every tiny crack in the standard model matters. Because we do not know where the next great insight will come from. It might come from a theorist scribbling equations on a blackboard at 3 in the morning. Or it might come from an experimentalist staring at a data plot at CERN, noticing something slightly off, something that does not quite fit. Every anomaly, no matter how small, is a potential doorway into the hidden layer. Let me now take you through one of the most profound ideas that connects all of these threads. The idea of vacuum structure. The vacuum, the empty space between atoms and between stars, is not empty. It is the most complex and mysterious object in all of physics. In quantum field theory, the vacuum is the ground state, the lowest energy state of all the fields that fill space. But this ground state is not zero. It is a seething, dynamic entity where virtual particles constantly pop into and out of existence, where fields fluctuate and interfere, where the very geometry of spacetime vibrates at the quantum level. The Casimir effect, demonstrated experimentally in 1997, is direct proof that the vacuum has structure. Two uncharged metal plates placed very close together in a vacuum will experience an attractive force. This force arises because the vacuum fluctuations between the plates are restricted by the boundary conditions they impose, creating a net pressure that pushes the plates together. The vacuum literally pushes things. It has energy, it has structure, it has consequences. And here is the problem. When you try to calculate the total energy of the vacuum using quantum field theory, you get a number that is absurdly large. The theoretical prediction for the vacuum energy density is roughly 10 to the 120 times larger than the observed value. This is the cosmological constant problem, and it has been called the worst prediction in the history of physics. No theoretical framework has ever been so spectacularly wrong. What does this have to do with the hidden layer? Everything. The discrepancy between the predicted and observed vacuum energy suggests that there is something about the vacuum that we fundamentally do not understand. Some mechanism is canceling the vast majority of the vacuum energy, leaving only the tiny residual that we observe as dark energy. But what is that mechanism? Is it a symmetry we have not discovered? Is it a property of the extra dimensions? Is it evidence that our entire framework for calculating vacuum energy is wrong? The vacuum could be the hidden layer. Everything we see, every particle, every force, every galaxy, could be a tiny perturbation on top of this vast, mysterious ground state. The universe we observe might be just the ripples on the surface of an ocean of vacuum energy, an ocean whose properties we barely understand. CERN probes the vacuum every time it smashes particles together. Every collision is in a sense a disturbance of the vacuum, a way of exciting the quantum fields and seeing what comes out. And the exotic results that emerge, the Higgs boson, the quark-gluon plasma, the exotic hadrons, are all manifestations of the vacuum's hidden structure. Now I want to address something that I know many of you are thinking about. The conspiracy theories, the fears, the wild claims that swirl around CERN like a fog, because no discussion of CERN would be complete without addressing them, honestly and directly. You have probably seen the headlines. CERN is opening portals to other dimensions. CERN will create a black hole that swallows the Earth. CERN is communicating with entities from another reality. These claims range from the misguided to the absurd, but they persist because they tap into something real, a genuine sense of awe and unease about the scale and power of what CERN does. Let me address the black hole fear first, because it is the most concrete. The concern is that LHC collisions could create a microscopic black hole that would grow and consume the Earth. This sounds terrifying, but it is wrong, and we know it is wrong because of a simple argument based on cosmic rays. Cosmic rays are high-energy particles, mostly protons, that rain down on Earth from space. Some of these cosmic rays carry energies far greater than anything the LHC can produce. The most energetic cosmic ray ever detected, the Oh My God particle observed in 1991, carried roughly 50 joules of energy in a single proton, equivalent to a fast baseball. That is millions of times more energy than the LHC can achieve. And these ultra-high-energy cosmic rays have been hitting the Earth, the Moon, the Sun, neutron stars, and every other object in the universe for billions of years. If high-energy particle collisions could create dangerous black holes, the universe would have been consumed long ago. The Earth has been bombarded by cosmic rays with energies far exceeding the LHC's capability for 4.5 billion years. And it is still here. This is not speculation, this is an observational fact. Furthermore, even if microscopic black holes could be created at the LHC, Stephen Hawking's theoretical work predicts that they would evaporate almost instantaneously through a process called Hawking radiation. A black hole with the mass produced in an LHC collision would have a lifetime of roughly 10 to the minus 27 seconds, far too short to interact with anything. Now, the ironic thing is that the creation of microscopic black holes at the LHC would actually be one of the most exciting discoveries in the history of science. It would be direct evidence that extra dimensions exist. In our ordinary 3+1 dimensional spacetime, the energy required to create a black hole is the Planck energy, roughly 10 to the 19 gigaelectron volts, far beyond the LHC's reach. But if extra dimensions exist, the effective Planck scale could be much lower, possibly within the LHC's range. So, if we ever did detect micro-black holes, it would not be a catastrophe. It would be a revelation. It would confirm the existence of extra dimensions and open an entirely new chapter in physics. As for the claims about portals and entities, there is a grain of truth buried under the sensationalism. CERN is genuinely searching for extra dimensions. The mathematics of string theory, the Randall-Sundrum model, and Kaluza-Klein theory all predict that extra dimensions might exist. But searching for the signature of extra dimensions in collision data is very different from opening a portal in a science fiction movie. The extra dimensions, if they exist, would manifest as specific patterns in the energies and angles of the particles produced in collisions. They would be inferred from data, not experienced directly. No one at CERN is opening doors to anywhere. The sensationalism around CERN is unfortunate because it distracts from the real story, which is far more interesting than any conspiracy theory. The real story is that we live in a universe that is 95% invisible. The real story is that the most successful theory in the history of science is incomplete. The real story is that the most powerful machine ever built is finding hints, real hints, backed by real data, that there is something beneath the surface of reality that we have not yet discovered. Let me tell you about the cost debate, because it is a question that comes up frequently and deserves a thoughtful answer. The LHC cost approximately $13.25 billion. The proposed Future Circular Collider would cost over $20 billion. Is it worth it? Here is something most people do not know. The World Wide Web was invented at CERN. In 1989, Tim Berners-Lee, a British physicist working at CERN, proposed a system for sharing information among scientists. That system evolved into the World Wide Web, which has since become the most transformative technology of the modern era, generating trillions of dollars in economic value and reshaping every aspect of human civilization. It was a byproduct of fundamental research. It was never the goal. It was an unexpected gift from the pursuit of knowledge for its own sake. This is the pattern of fundamental science. The people who developed quantum mechanics in the early 20th century were not trying to invent the transistor, or the laser, or the LED, or the MRI machine. They were trying to understand the behavior of atoms. But the understanding they gained, the equations they wrote, the principles they discovered, became the foundation for technologies that have transformed the world. Every single electronic device you use, every medical imaging technique, every fiber optic cable, every semiconductor chip, traces its ancestry back to fundamental research that seemed useless at the time. The same is true for CERN. Beyond the World Wide Web, technologies developed at CERN have found applications in medical imaging, particularly PET scans, which use the same positron annihilation physics that CERN studies. CERN's work on superconducting magnets has advanced the technology used in MRI machines and fusion reactors. CERN's massive computing challenges have driven advances in distributed computing, data analysis, and artificial intelligence. And these are just the technologies we have found so far. If CERN or its successor experiments discover the nature of dark matter, or confirm the existence of extra dimensions, or find evidence that spacetime is emergent, the technological implications would be impossible to predict but potentially revolutionary. Understanding a new aspect of reality always, eventually, leads to new technologies. The only uncertainty is how long it takes. Now, let us talk about the future, because the search for the hidden layer is about to enter a new and exciting phase. As I speak to you now, the Large Hadron Collider is in its final months of operation before a major transformation. The last proton collisions of 2026 were recorded on March 7th, and the machine will continue running until the end of June, squeezing out every last drop of data before it goes silent. At the end of June 2026, the LHC will begin a 4-year shutdown called Long Shutdown 3. During this period, part of the LHC will be dismantled and replaced with innovative new equipment designed to transform it into the High Luminosity LHC, or HL-LHC. This upgraded machine, expected to begin operating in 2030, will increase the collision rate by a factor of 10 compared to the current LHC. This means 10 times more data, 10 times more chances to find rare processes, 10 times more statistical power to confirm or deny the anomalies that are currently tantalizing the physics community. Already, CERN has reached major milestones in this upgrade. In February 2026, cryogenic testing began on a full-scale magnet system for the HLLHC, cooling a 95-meter string of superconducting magnets to minus 456 degrees Fahrenheit. These tests are validating the performance of the innovative technology that will be at the heart of the upgraded accelerator. The HLLHC will be able to measure the Higgs boson's properties with unprecedented precision, potentially revealing deviations from the standard model that are too small to see in current data. It will search for rare decays with sensitivity that is orders of magnitude beyond what is currently possible. It will push the searches for dark matter, extra dimensions, and exotic particles into uncharted territory. If the hidden layer exists at energies accessible to the LHC, the HL-LHC will find it. But the ambitions of the physics community extend far beyond the HL-LHC. In March 2025, CERN released the feasibility study for the Future Circular Collider, or FCC. This proposed next-generation machine would be 91 kilometers in circumference, more than 3 times the size of the LHC, and it would be built in the same region of Geneva, in a new tunnel deeper underground. The FCC would operate in 2 phases. The first phase, called FCC-EE, would be an electron-positron collider, designed to make precision measurements of the Higgs boson, the W and Z bosons, and the top quark with accuracy far beyond anything achievable at the LHC. Electron-positron collisions are much cleaner than proton-proton collisions, producing far less background noise, which makes precision measurements possible that would be hopelessly muddled in the LHC's environment. The second phase, called FCC-HH, would be a proton-proton collider operating at an energy of approximately 100 teraelectron volts, roughly 7 times the LHC's current energy. At these energies, the FCC-HH could directly explore the zeptouniverse, producing particles that are too heavy for the LHC to create and probing distances that are currently inaccessible. In November 2025, the CERN Council reviewed the feasibility study and concluded that the FCC would provide the platform for a visionary physics program addressing many of the open questions in particle physics. A decision by CERN's member states is expected by 2028, with construction potentially beginning in the early 2030s. The electron-positron phase could begin operating in the 2040s, and the high-energy proton-proton phase would follow in the 2070s or beyond. I know what you might be thinking. The 2070s? That is nearly 50 years from now. Is it worth planning that far ahead? And the answer is emphatically yes. The LHC itself was first proposed in the 1980s and did not produce its first physics results until 2010. The Higgs boson was predicted in 1964 and discovered in 2012, 48 years later. Fundamental science operates on timescales that dwarf the timescales of politics, economics, and individual careers. And the payoff, when it comes, is immeasurable. But we do not have to wait until the 2070s for progress. There are experiments that can probe the hidden layer right now, using different techniques and different facilities. The muon collider concept is one of the most exciting developments in accelerator physics. Muons are heavier than electrons, which means they lose much less energy to synchrotron radiation when bent in a circle. This makes it possible to build a circular collider that reaches much higher energies in a much smaller footprint. A muon collider with a circumference of just a few kilometers could reach the same energies as the proposed FCC. The challenge is that muons are unstable, decaying with a lifetime of about 2.2 microseconds, which means they must be produced, cooled, accelerated, and collided before they decay. This is an extraordinary technical challenge, but recent advances have made it seem increasingly feasible. A muon collider design study is currently underway, with the goal of demonstrating the key technologies within the next decade. Beyond colliders, there are dark matter direct detection experiments. These experiments, located deep underground to shield them from cosmic rays, use massive detectors filled with ultra-pure xenon or other materials to look for the faint signal of a dark matter particle colliding with an atomic nucleus. The xenon experiment, located at the Gran Sasso National Laboratory in Italy, the LZ experiment at the Sanford Underground Research Facility in the United States, and the Pandax experiment in China are all pushing the sensitivity of these searches to unprecedented levels. If dark matter consists of WIMPs with masses and interaction strengths within the remaining allowed parameter space, these experiments could detect them within the next few years. Neutrino experiments are another crucial piece of the puzzle. Neutrinos are the most mysterious particles in the Standard Model. They have mass, but the Standard Model originally predicted they should be massless. The discovery of neutrino oscillations, the phenomenon where neutrinos change from one type to another as they travel, proved that they have mass and won the Nobel Prize in 2015. But the mechanism that gives neutrinos their mass is unknown. It could involve entirely new particles, such as heavy sterile neutrinos, that could also serve as dark matter candidates. The DUNE experiment, currently under construction in the United States, will study neutrino oscillations with unprecedented precision by sending a beam of neutrinos from Fermilab in Illinois to a massive detector located 1.5 kilometers underground in a former gold mine in South Dakota, 1,300 kilometers away. DUNE will measure the properties of neutrino oscillations precisely enough to determine whether neutrinos and antineutrinos oscillate differently, which would be evidence of CP violation in the neutrino sector. If this CP violation is large enough, it could help explain the matter-antimatter asymmetry of the universe. The Hyper-Kamiokande experiment in Japan, which began operations recently, will also study neutrino oscillations with extraordinary sensitivity. Its detector, a cylindrical tank filled with 260,000 tons of ultra-pure water, is the largest water Cherenkov detector ever built. When a neutrino interacts with a water molecule, it produces a charged particle that travels faster than the speed of light in water, emitting a cone of Cherenkov radiation that can be detected by the thousands of photomultiplier tubes lining the detector walls. Gravitational wave detectors, originally designed to observe the mergers of black holes and neutron stars, are also becoming tools for fundamental physics. The LIGO and Virgo observatories, along with the newer Kagre detector in Japan, have opened an entirely new window on the universe by detecting the ripples in spacetime produced by the most violent events in the cosmos. Future gravitational wave observatories, such as the space-based LISA mission planned by the European Space Agency and the proposed Einstein telescope in Europe, will be sensitive to gravitational waves at different frequencies, potentially detecting signals from phase transitions in the early universe that could reveal the existence of new physics. And then there are quantum sensors, a rapidly developing technology that uses the extreme sensitivity of quantum systems to detect tiny changes in their environment. Atomic clocks, atom interferometers, and quantum magnetometers are all being explored as tools for fundamental physics. Some of these devices could be sensitive enough to detect the effects of dark matter particles passing through them, or to measure the gravitational constant with enough precision to reveal deviations from general relativity. The search for the hidden layer is not a single experiment at a single laboratory. It is a global enterprise, spanning dozens of countries, hundreds of institutions, and thousands of researchers. Every approach, from the highest energy collisions at the LHC to the most delicate quantum measurements in a tabletop experiment, provides a different view of the same underlying mystery. And it is the combination of all these approaches, the convergence of evidence from multiple independent sources, that will ultimately reveal what lies beneath the surface of reality. Let me now take you into the philosophical and existential territory that this journey inevitably leads to. Because the question of whether there is a hidden layer beneath reality is not just a scientific question. It is a question about the nature of human existence. It is a question about what it means to be a conscious being in a universe that is vastly larger and stranger than our senses evolved to comprehend. Consider this. Your eyes can detect electromagnetic radiation only in a tiny range of wavelengths, from about 400 to 700 nanometers. This is the visible spectrum, the colors of the rainbow. But the electromagnetic spectrum extends from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than an atomic nucleus, a range of more than 20 orders of magnitude. You can see less than 1/1,000,000th of the electromagnetic spectrum. Your ears can detect sound waves in a frequency range of about 20 to 20,000 hertz. But sound waves exist at frequencies far below and far above this range. Dogs can hear frequencies up to about 65,000 hertz. Bats use ultrasonic frequencies up to about 200,000 hertz. You are missing most of the auditory world. Your sense of touch can detect objects down to a fraction of a millimeter, but atoms are about 1/10,000,000,000th of a meter, and subatomic particles are smaller still. You cannot feel the microscopic world. Your biological senses evolved not to show you reality as it truly is, but to show you just enough of reality to survive and reproduce. Evolution did not optimize us for truth. It optimized us for fitness. And there is no guarantee that the slivers of reality our senses can access give us an accurate picture of the whole. This is why science is so extraordinary. It is a systematic method for extending our senses far beyond their biological limits. Telescopes let us see billions of light years into space. Microscopes let us see the structure of individual cells and molecules. Particle colliders let us probe the subatomic world at scales millions of times smaller than an atom. And the mathematical language of physics allows us to describe aspects of reality that have no direct sensory analog: quantum superposition, spacetime curvature, field configurations, entanglement, concepts that no human eye has ever seen and no human hand has ever touched. When we talk about a hidden layer beneath reality, we are talking about the possibility that our current scientific instruments, as extraordinary as they are still showing us only a fraction of what exists. We know this is true in a quantitative sense, since dark matter and dark energy constitute 95% of the universe's mass energy content. But it might also be true in a qualitative sense. There might be entire aspects of reality, entire types of structure and organization that our current theoretical frameworks cannot even describe. This is not a failure of science, it is the frontier of science. Every great advance in physics involved a conceptual revolution, a moment when we realized that our previous framework was not wrong but limited, a special case of something more general. Newton's mechanics is a special case of Einstein's relativity, valid only at speeds much less than the speed of light, and in gravitational fields much weaker than those near black holes. Classical physics is a special case of quantum mechanics, valid only for systems with large numbers of particles where quantum effects average out. And the Standard Model itself might be a special case of a deeper theory, valid only at energies much less than the Planck scale, and in conditions where the hidden layer's effects are negligible. What would it mean to discover this deeper theory? What would it mean to peel back the surface of reality and see what lies beneath? Historically, every such discovery has been both intellectually thrilling and practically transformative. When we discovered that atoms were not indivisible but had internal structure, we gained the ability to manipulate matter at the atomic level, leading to nuclear energy, the periodic table, and modern chemistry. When we discovered quantum mechanics, we gained the ability to understand and control the behavior of electrons in solids, leading to the transistor, the semiconductor, and the information age. When we discovered the structure of DNA, we gained the ability to understand and modify the genetic code, leading to modern medicine, agriculture, and biotechnology. Each of these discoveries revealed a hidden layer beneath what was previously thought to be the foundation. And each one transformed civilization in ways that could not have been predicted in advance. If we discover the nature of dark matter, or the structure of extra dimensions, or the mechanism by which spacetime emerges from quantum information, the implications would be equally unpredictable and equally transformative. Could understanding dark matter lead to new forms of energy? Could manipulating extra dimensions enable faster-than-light communication or travel? Could mastering the relationship between quantum information and space-time lead to technologies that seem like magic from our current perspective? I do not know. No one knows. And that is exactly the point. The history of science tells us that understanding a new aspect of reality always, eventually, leads to capabilities we could not have imagined beforehand. The hidden layer, whatever it turns out to be, is not just an abstract intellectual puzzle. It is the next great frontier of human capability. Now, I want to address a question that I know is on many people's minds, because it appears in every discussion of fundamental physics and the hidden layers of reality. The simulation hypothesis. The idea that our universe might be a computational simulation running on a computer in some higher-level reality. This idea was given its modern form by the philosopher Nick Bostrom in 2003, who argued that at least one of the following three propositions must be true. 1. Almost all civilizations at our level of development go extinct before becoming technologically mature. 2. Almost all technologically mature civilizations are not interested in running ancestor simulations. Or 3. We are almost certainly living in a computer simulation. The logic is straightforward. If technologically mature civilizations exist and are interested in simulating their past, then the number of simulated beings would vastly outnumber the number of real beings, and so any randomly selected conscious entity is overwhelmingly likely to be simulated rather than real. Does CERN's search for hidden layers have anything to do with the simulation hypothesis? In a sense, yes, and in a sense, no. If reality has a granular structure at the Planck scale, as some theories predict, this could be interpreted as evidence of a computational grid underlying the simulation. If there are constraints on the physics that cannot be explained by any deeper principle but seem arbitrary, this could be interpreted as parameters set by the simulators. And if CERN discovers that spacetime is emergent, that it arises from a more fundamental substrate of quantum information, this might be seen as consistent with a computational framework. But most physicists are skeptical of the simulation hypothesis, and for good reason. It is not clear that the concept of computation, which depends on the physical substrate of a computer, can be applied to the universe itself without circularity. The laws of physics that govern a simulation must be implemented in a physical computer, which is itself subject to laws of physics, raising an infinite regress. And the simulation hypothesis as currently formulated makes no specific testable predictions. It is not a scientific theory but a philosophical conjecture. That said, the connection between information theory and fundamental physics is genuine and profound. The holographic principle, the black hole information paradox, the role of entanglement in space-time geometry. These are all real scientific ideas that suggest that information is not just a way of describing reality, but is, in some deep sense, woven into the fabric of reality itself. Whether this means we live in a simulation is a question that science cannot currently answer. But the role of information in fundamental physics is real, and it is one of the most active and exciting areas of research in theoretical physics today. Let me now talk about consciousness, because it is the elephant in the room of any discussion about the nature of reality. We are conscious beings trying to understand a universe that somehow gave rise to consciousness. And the relationship between consciousness and physics is one of the deepest unsolved problems in all of science. The hard problem of consciousness, as formulated by the philosopher David Chalmers, is the question of why and how physical processes in the brain give rise to subjective experience. We know that neurons fire, that neurotransmitters are released, that brain regions activate in response to stimuli. We can describe these processes in exquisite detail using neuroscience. But none of this explains why there is something it is like to see the color red, or to feel the sensation of warmth, or to experience the emotion of joy. The qualitative, first-person aspect of consciousness, the felt experience, seems to be something that our current physical theories cannot account for. Some physicists have proposed that consciousness might be connected to fundamental physics in ways we do not yet understand. The most well-known of these proposals is the orchestrated objective reduction theory, developed by the physicist Roger Penrose and the anesthesiologist Stuart Hameroff. They propose that consciousness arises from quantum processes in microtubules, tiny protein structures inside neurons. According to their theory, quantum superpositions in microtubules undergo a special type of wave-function collapse, orchestrated by the biology of the brain, that gives rise to conscious experience. This theory is controversial, to put it mildly. Most neuroscientists and physicists are skeptical, arguing that the brain is too warm and wet for quantum coherence to be maintained for the timescales required. However, recent experiments have shown that quantum effects can persist in biological systems, such as in photosynthesis and avian navigation, at temperatures higher than previously thought possible. The debate is far from settled. What does this have to do with the hidden layer? If consciousness is connected to quantum physics at a fundamental level, then the hidden layer beneath reality might be relevant, not just to physics, but to the nature of mind itself. If spacetime is emergent, if reality at its deepest level is a network of quantum information, then consciousness, as a phenomenon that seems to involve information processing in a fundamental way, might be more deeply connected to the fabric of reality than we currently understand. I want to be clear that this is highly speculative. We do not have a scientific theory of consciousness that makes testable predictions in the context of fundamental physics. But the question is genuine, and it is one that the discovery of a hidden layer might eventually help illuminate. If we can understand what reality is made of at its most fundamental level, we might also gain insight into how that reality gives rise to the experience of being a conscious observer within it. Now, let us talk about one more fascinating concept that connects to the hidden layer, the anthropic principle and the fine-tuning of the universe. The laws of physics, as we observe them, appear to be extraordinarily fine-tuned for the existence of complex structures, including life. If the mass of the Higgs boson were slightly different, atoms could not form. If the strong force were slightly weaker, nuclei could not hold together. If the cosmological constant were slightly larger, the universe would have expanded too quickly for galaxies to form. If it were slightly more negative, the universe would have collapsed back on itself long ago. The list of fine-tuned parameters is long, and the degree of tuning required is, in many cases, extreme. Why is the universe fine-tuned for life? There are several possible answers. One is the multiverse. If there are an enormous number of universes, each with different physical constants, then we naturally find ourselves in one where the constants are compatible with our existence. We cannot observe the other universes where the constants are wrong, because in those universes there is no one to observe anything. This is the anthropic selection effect. The multiverse is a natural consequence of several theoretical frameworks. Eternal inflation, the idea that the process of cosmic inflation is still occurring in most of the universe, creating new bubble universes with different physical constants, predicts a multiverse. String theory, with its landscape of 10 to the 500 possible configurations, predicts a multiverse. If the multiverse exists, the fine-tuning is not fine-tuning at all, it is selection bias. Another possibility is that there is a deeper principle, not yet discovered, that constrains the physical constants to have the values we observe. Perhaps the hidden layer, whatever it turns out to be, does not allow for arbitrary parameter values. Perhaps the structure of the deeper theory is such that the constants of the standard model are determined, not free parameters. This would be the most intellectually satisfying resolution, but it is also the most ambitious. It would require a theory of everything that not only unifies all the forces, but also predicts the values of all the parameters. CERN's role in this quest is to constrain the possibilities. Every precision measurement of the Higgs boson's properties, every search for new particles, every test of the standard model's predictions narrows the space of possible deeper theories. The hidden layer, whatever it is, must be consistent with everything CERN has already observed. And that is a very powerful constraint. Let me bring all of this together now, because we have covered an enormous amount of ground, and I want to make sure the full picture is clear. We started with a question. Has CERN discovered a hidden layer beneath reality? The honest answer is that CERN has not made a single definitive discovery that proves the existence of a hidden layer. There is no smoking gun. There is no single experiment that, by itself, overturns the standard model and reveals the deeper truth. But that is not the whole story, because what CERN has done, through decades of extraordinary experimental work, is build an overwhelming case that the standard model is incomplete. The evidence comes from multiple independent directions. The muon's magnetic moment, studied with unprecedented precision by the Fermilab experiment, has revealed tensions within the theoretical predictions themselves, suggesting that the hadronic sector of the standard model may be more complex than previously understood. The searches for new particles have not found the candidates that theorists most expected. Supersymmetric partners and WIMPs, which tells us that if the hidden layer exists, it is not structured in the simplest way our theories predicted. The LHCb experiment has discovered a zoo of exotic hadrons, tetraquarks, and pentaquarks that reveal unexpected richness in the strong force. The study of ultra-rare decays, the Magnificent Seven of Andrzej Buras, is beginning to provide indirect access to the zeptouniverse, a realm beyond the direct reach of the LHC. The FACER experiment is pioneering a new approach to searching for dark sector particles. The antimatter experiments at CERN's antimatter factory have achieved the first antimatter qubit, opening a new window into the matter-antimatter asymmetry. And the study of entropy and proton collisions has revealed a hidden order beneath the apparent chaos, confirming the deep principle of unitarity in the most extreme conditions ever created in a laboratory.